Hello, everyone.
Hello.
Hello.
Sorry, I connected earlier and some reason it wouldn't let me go back to my screen and only gave me a choice of to leave meeting or just sit there and stare at a blank screen. So I had to back out.
Yeah, it said ended by host, and I was like, huh.
Yeah, yeah, it was kind of weird. That's the problem with letting us old people handle technology. So I'm waiting for more people to come in. I just made, I decided to go ahead and do a last test. That'll be due by Wednesday at 11:59 p.m. And that's, I think I called it test 7, and it's chapters 37, 38, and 39, which between YouTube and what I cover in class this time and next time, you should have enough material to follow what you need to do on that test. But it's still going to count as an extra one. So I think I originally said I would drop one of your lowest online tests. Now I'm adding that one, but I'm dropping 2. So technically you don't have to take it, but why wouldn't you? Because you get an infinite number of tries and only count your highest. So it's something worthwhile. Since the final is comprehensive, it'll help you for that too. Don't know what this is. Okay, I'm going to kill that. Right, let's see what's going on here. Okay, that wasn't what I needed. I'm looking for something. Where it went? That was not it. Oh, I remember. Okay. Let me check somewhere else. Hold on. So what I was looking up, I was trying to look up in my channel what I have on quantum mechanics. Some are just called some's called quantum mechanics. I think another one's called early quantum mechanics. But I did post the list of all the titles, so you can just open up that text document up at the top, and that'll show you all the ones that are available to you listed by physics. Some are astronomy, but like I said, they have a whole separate section for the astronomy ones from the physics ones. So you can just flip through the physics ones looking for that. I'm actually flipping through the titles right now to see if I remember, if I was correctly remembering what they were called. I've done several of them. I need to do a lot more. I did proton in an infinite well model for gamma decay. So that's just a simple analysis of quantum mechanics using Schrodinger Equation, a very simple one that they do with undergraduates and people in your class level, basically. And with that, you can automatically predict that the energy released by letting a photon emanate from an actual nucleus is going to be in the gamma ray area. So that's kind of a cool one. Particle and infinite well, probability density, better Compton effect derivation, the Bohr atom, and the hydrogen spectrum. Those are all titles that are relevant. I just had to scroll to the list and then scroll down almost to the end. I know there's some more. No, cannon fire, driving, relativistic, using friction, atwood machine, dielectric, electric flux, dipole, coulombs, scientific notation, half-life measurement and uncertainty, quantum mechanical, atom, and intro to radioactivity. So that's another one, quantum mechanical, atom, and an intro to relativity. That actually, no, that's more of an astronomy related one, but it is helpful for helping you learn. And then, of course, you still have the, Crash Course Physics that covers quantum mechanics. That might help you as well. So anyways, you can look at the top of our Canvas page, and in the important links and documents section, that's where you'll find my text list of not only the names of the episodes or the posts that I did on my YouTube channel, but you also find the actual YouTube address, so you can pull that up if you want. I might have named them all already because I'm not seeing any other ones jump out at me. Nope, I just got to the bottom. So yeah, that must have been all of them. So anyways, you guys can start on that. Does anyone have any questions about this and what's going on now? Looks like I got one extra person, so now we're actually up to 7 students instead of 6 students and me. So wow, yay, woo. Okay, So what I wanted to start off with tonight is that we're going to talk about chapter 37, which is called, let's go back to the beginning of the chapter. It was called Early Quantum Theory and Models of the Atom. So this sort of sets the mood for what was happening in physics in the late 1800s, early 1900s, and gives you an idea how we got to certain places. And it's kind of neat. It's almost like the universe handed us these little, like almost like they handed us a step ladder where we could step up and see just over the edge of the countertop looking into the sink, but not see the whole thing. And what we saw was completely wrong, but it got us thinking in this weird way that was consistent with reality. And then ultimately Bohr was able to take that and run with it and develop quantum mechanics as we know it today. So it's kind of a neat story from a historical standpoint. And I will, of course, discuss the history of it. Hold on a second. I get another pad because I'm down to my last sheet on that one. Ooh, that's not good. Okay. So I got another pad. So let me discuss what's going on. So in the late 1800s, early 1900s, I've mentioned this several times before, but basically everybody thought that they were probably, no problem, Jacob, that they were probably about finished. In other words, we figured out everything. Science was made up. Or Newton and Maxwell got us basically everything we need to know. We have Newton that gives us all the classical theory, which we didn't call classical at the time, but it's basically just physics. You know, F equals ma, F equals dp dt, torque equals I d omega over dt, stuff like that. And it was more a matter of, they said they were probably going to solve some problems that are, you know, more difficult to solve than others. Maybe they take a special kind of differential equation or something like that. And they're just going to make sure that their answers are right to, you know, 10 decimal places instead of 3 or something weird like that. And I suspect most scientists would have answered that way in the late 1800s, early 1900s. But basically, Einstein comes along and he sees a problem that no one else really sees. Some other people were playing with this, with some of the mechanisms about relativity that ultimately turned out to be relativity, but no one really seemed to have a big picture understanding of what was going on. But Einstein did. Einstein had looked at Maxwell's equations, and Maxwell's equations were well accepted by this time. So everybody had access to them, just like Einstein did. But Einstein was a big fan, thought Maxwell was brilliant, and of course he was. And what he found out was when you put together Maxwell's equations, they make a wave, which I've shown you guys and also have a derivation of in the videos. But in that wave equation, there was a very specific spot where the velocity goes, and that wave equation turned out to show you that basically radiation was a wave basically oscillating in two ways. So you had an electric field oscillating, let's say vertically, and then when the electric field was up, at the same time, the magnetic field would be to the right. And then when the electric field was down, the magnetic field would be to the left. And while all that's going on, the wave would be propagating forward. So it's really an oscillation of electric field in 2 dimensions, oscillation of a magnetic field in 2 dimensions, and then a propagation in a 3rd dimension, all 3 of which are perpendicular to each other. That's at that instant, he knew not only that light was a wave, but he knew exactly what it was. So we'd gone sort of full circle. We thought of light as waves, and then Newton more or less derives everything we know, even to this day, other than some quantum mechanical results. Newton was able to derive all the equations for optics, treating light as a bunch of particles. Huygens comes along, shows us it's a wave, or had shown us and stuff of that sort. But now Maxwell's coming along and saying, hey, here it's a wave, and this is the property. And lo and behold, these 2 constants, epsilon 0 and mu 0, when you multiply them, take the square root of the answer and then flip it over, that turns out to be the speed of light, right? So that's pretty amazing. And that's pretty much all there was with science. But Einstein took those wave equations and looked at them and realized, wait a second, there's no change in the wave equation if you apply it to a system, say, moving along at 300 miles per hour or 300,000 miles per hour or 300 million miles per hour. There was no change to the equation. And from that, he kept thinking of these physical experiments he could do. Gedanken's what he called them, thought experiments. And those thought experiments were giving him things that were basically paradoxical. So, you know, 2 things that were equally valid according to modern science, but were impossible to both happen simultaneously. One's got to be right and the other one's got to be wrong. That's what a paradox was. And he was seeing stuff like that. Like he would see, one of his ideas was riding a light beam and then trying to shave in front of a mirror. He was getting this idea that, you know, you wouldn't be able to see your own image, or if you did, it, you know, it would be kind of instantaneous and some weird stuff like that. Just a bunch of little anomalies that he didn't like. So he basically said, okay, well, Maxwell's equation is telling us that the speed of light doesn't change. Maybe that's the fundamental idea. And he put together his, you know, those two postulates, which says the speed of light is a constant independent of the motion of the source and the observer. And then the second one was that the laws of physics are the same for all inertial observers. And boom, out from that pops special relativity. The next day, there's an appendix he sends out. He said, oh, by the way, I wanted to add this to my paper. It's an appendix. I discovered that E equals mc squared, which of course was actually able to be used to show how the sun lives, because at that time we only thought the sun was possibly up to 50,000 years old. People were starting to question that, though, because the biological and geological sciences were suggesting a much older Earth, you know, maybe hundreds of thousands of years old. And Lord Kelvin's calculation, treating the sun as a lump of coal, would only allow it to live for about 50,000 years. And according to Genesis, we're on par with that. That's no big deal, because according to Genesis, if you add up the begats and, you know, how old the person was when they begat such and such a person, until it runs into someone that was a historical figure that you know when they live, which in this case happened to be Nebuchadnezzar. When they did that, they figured out that the universe was probably around 8,000 years old, basically. So if the Earth lives for 50 years, the universe, that is, lives for 50,000 years, then clearly we're fine. But when you start thinking about something lasting 100,000 years or 1,000,000 years to explain, for instance, plate tectonics, which was, you know, literally not really taken on seriously until probably the late 60s, early 70s. But finally, they did accept that as well. So plate tectonics was one thing, evolution was another thing, and all these things were taking hundreds of thousands and even millions of years, tens of millions of years. So Einstein's coming up with E equals mc squared was really the answer to how the sun burns. It actually allowed us to make nuclear weapons, which is, you know, as good or as bad as you think they are, and to build other types of nuclear weapons, to use nuclear power, all that good stuff. So it's a really big undertaking. So that was one thing, and it was done by one guy. I mean, other people wrote things that were important to it, but really the whole thing came out as a finished product that literally September 2015, we finally confirmed yet another piece of the general theory of relativity that he published not in 1905, but in 1915. So that's amazing. The other part is what we're going to talk about now, and that's really the quantum mechanical revolution. And Einstein, lo and behold, was part of that, even though he fought it until the day he died. Literally, they found him lying in his bed, dead. He was already in bed rest because, you know, he knew he was a terminal and everything. And on his notebook was him scratching yet more equations, trying to find field equations that would make quantum mechanics not necessary. So literally, he died, you know, fighting the essence of quantum mechanics, even though he's one of the founding fathers of it, by writing his Photoelectric Effect, which, by the way, was the paper in 1905 that he won the Nobel Prize for. So pretty remarkable events. There was a few mysteries in the background of all this stuff, where everybody was thinking science was okay, and that it was so worked out that we were just going to figure out more decimal places. And one of the issues was something they called the ultraviolet catastrophe, where basically when you got into the ultraviolet portion of the spectrum, the equations that told you how matter is supposed to project radiation didn't work. Okay, so let me flip my document cam on for a second so you can see what I'm talking about. So if you actually make a plot, say, of the energy, intensity of energy put out as a function of wavelength or frequency, let's do wavelength. So if you actually make such a graph, what happens is you make a graph of I, the intensity, and this pink might not be a good color, and that focus is horrible. Okay, let's do this now. So this is the intensity. This is like the amount of energy per square meter of radiation coming from an object that's hot enough to produce radiation in whatever part of the spectrum you want. This is the wavelength. And what everybody knew was that basically the distribution of these energies should go steeply up at low wavelengths, reach some peak, and then gradually fall down like that. Okay. So it's real steep on the low frequency side, or the low wavelength side, and gradual on the high wavelength side. And we had, for instance, a nice equation that described that pretty well, and that was called the Rayleigh-Jeans equation. Rayleigh-Jeans, hopefully I'm spelling that right. Yes, I did. Rayleigh-Jeans equation. There was another equation that sort of worked around here, and that didn't really fit right either, and that was from Wien, W-E-I-N. And basically the equations that fit this part didn't match the equations that fit this part, so there was no one equation. So in comes a guy by the name of Max Planck, P-L-A-N-C-K. So Max Planck was a very, traditional physicist. He wasn't a revolutionary in any sense. In fact, he was quite old by the time he did this. So in 1900 was the year he did it. But basically, he analyzed, let's say, a horseshoe stake. If you take a horseshoe stake and you put it in a fire, it initially just looks like a rusty piece of iron because that's what it is, right? But as you leave it there longer and longer and longer, the iron will actually start to reach a high enough temperature that the radiation it puts off is in the visible spectrum. And that's what this curve represents. Like some of this frequency might be in the infrared, and some of this might be in the ultraviolet and stuff like that. It can, in fact, go all the way to, on this side, it would go all the way to radio waves. Actually, on this side, it would go all the way to radio waves. And on that side, it would go all the way to gamma rays. All of those are possibilities. So he was trying to analyze metals to see how he could get this a curve. And he did a trick that's often done. And it's basically when you're trying to deal with a continuous variable, like in this case, intensity doesn't go stepwise from one wavelength to another wavelength to another. It actually covers all the wavelengths, say between 1 meter and 2 meters, and all of them between 1,000 meters and 1,001 meters. So it's a continuous variable. But what he did was he imagined it was a discrete variable, sort of like you'd say, okay, E is equal to some integer times h times frequency. In other words, he knew the energy was related to the frequency, and he just put a constant in there, and then he put an n where n is equal to 0, which is not meaningful, 1, 2, 3, ... And the idea is when you do this kind of trick mathematically, in the end, you're supposed to take the limit as n goes to 0, and then that creates back a continuous variable. So him, in doing that, kept getting something that looked really promising, but as soon as he do that mathematical trick to get it back where it was, it fell all to crap. So finally he just said, screw it. I know I can leave it here, and this equation looks really good. And it turns out now we know to be the right equation. And it's basically the intensity as a function of wavelength and temperature is actually equal to 2 pi times h, which is that same h that I'm showing you there. We now name it Planck's constant. C squared, for c being the speed of light, lambda to the -5th power, all of that divided by e to the hc over kt over lambda kt minus 1. So this is the actual equation you got. And when you actually make a plot of that, it actually fits this curve perfectly. Not only that, if you do things like take the derivative of the intensity and set it equal to 0, it'll actually give you the wavelength at which this peak occurs. And that turns out to be, in fact, inversely related. In other words, large wavelength means low temperature, and low wavelength means high temperature. So it turns out that the wavelength of the peak is inversely proportional to the temperature. That's Wien's law. It's the same guy, but not the law we were talking about when he had an equation to fit this. But part of this equation can be gotten by Wien's law. And this is like the modern day thermometers where they just quickly stick it against your forehead and it gives you your temperature, or they quickly stab it in your ear and like within 2 seconds it gives you your temperature. So what they're doing is they're literally like making a plot like this, or doing the equivalent of making a graph like this, and then finding the wavelength at which the peak occurs, and then using Wien's law formula, which your book actually have. It's actually lambda is equal to 2.90, I think, times 10 to the -3rd. and that actually turns out to be in meters times Kelvin, all that divided by T. So this is what happens when you take the derivative of this and set it equal to 0 and then solve for the lambda in that equation. You get an expression that tells you exactly what wavelength this peak occurs at, and this is the formula that comes out. Okay. So he did get this equation, and of course, he told people, you know, I don't really know why this is, but it's as if energy only comes out in discrete amounts, and those things were called quanta. So we started calling them quantums of energy or quanta of energy, and they turned out to be photons. Photons have a energy equal to h times f, or if you look at this equation, you can see hc over lambda. That's another version of the energy, hc over lambda, because using velocity equals wavelength times frequency, where velocity is equal to the speed of light, you can see that frequency is really c over lambda. So if I took hf and replaced the f with c over lambda, then I get hc over lambda. So that's another famous equation. Again, it would have to be an integer multiple of that, but the main thing is the formula is hf, and the fact that it was integer multiples just told us something about nature and how it was quantized. There's certain allowed values of energy, and then there's other ones between those that aren't allowed at all. This constant, Planck's constant, it's actually a very small number. It's 6.6 times 10 to the negative 34. Hold on, 6.63. I just wanted to make sure I didn't mix up the units I was using. 6.63 times 10 to the negative 34. And the units for that, it's kind of a weird unit, but it's a joule times a second. 6.63 times 10 to the negative 34th joules times seconds. There's other values if you want it, for instance, in electron volts or something like that. There's other values you can use. And a lot of times we use h bar, which is defined to be h over 2 pi. So if you just divide this number by 2 pi, that's h bar. So anyways, those are some things that can come out. So now you know what this h is. And you can see, because this number is so small, you can see why we never noticed. Because, you know, there's a very few frequencies that you could multiply by 10 to the negative 34th and get a really decent sized number. So the difference between one of those and 1,000 of those is really, really teeny. Hence, the small number has made it almost impossible to see the details. But it's like those of you who drive a car with a digital speedometer, when you go to speed up, you'll notice it like skips, unless you got a Prius or something with no pickup. It basically skips certain speeds on the speedometer as it's speeding up. Now, in reality, that's not doing it because of quantum mechanics. It's doing it because the electronics is too slow to keep up, even with the acceleration of the vehicle. But still, it's a effect that's not unlike the real effect, which is there are certain kinetic energies that things can have that, and then there's ones that they can't have. And you can't just say it's going to have this amount of energy. It has to be some n times h times f. So that was really a big deal. He won the Nobel Prize for it, and it solved the ultraviolet catastrophe. So that's the ultraviolet. There should be an I there, violet catastrophe. And that was more about the frequency or wavelength of the wave of the radiation curve that you're expecting. Now that was one issue. But again, people didn't necessarily think that was a big deal. They thought it was just a matter of they got to work out the details. And Planck did this by analyzing the individual atoms in matter as if they were connected. You know, like this atom would be connected to its next atom by a spring, and then that one be connected to another one by a spring. And in fact, that row of atoms would be connected to another row of atom by strings, and then that plane of atoms would be connected to another plane of atoms by springs coming out of each of the atoms. And then he just did a statistical analysis of all that and got this famous equation. I do not expect you to memorize this equation, and you will see in your homework and stuff how you could actually, that E was supposed to be in there, sorry about that. You can see how it's supposed to be used, but it's a really difficult equation to deal with in general. If you want to take time to graph it with Desmos using the real values of lambda, you can see what the curves look like, stuff like that. But I think you will see that this equation can be used. E equals HF, E equals HC over lambda. Those equations can be used as well. So just make sure you have these in your equation sheet. This one up here, like I said, if I make you do some calculation with that, I will actually give it to you. So if you don't see it given in the problem, you can assume that's not what I'm asking you to use. Does that make sense? So that was one big problem that was studied and gave us an insight to some new physics coming around. This is sort of the first thing that people see and say, okay, well, this is kind of weird, but now we've got something that looks entirely different from Newton's equations, and it seems to work in that we got a curve that matches reality. Okay, well, about that same time, of course, Einstein's looking at this, and Einstein's got several problems he's thinking about. One of them's Brownian motion. Anybody familiar with that? Brownian motion. Originally, what was seen was people had found pollen on the surface of a liquid like water. The little pollen particles would zig and zag sort of erratically in random directions and stuff, and continue doing that. For some time, many people thought it was because it was pollen, so it was actually life, and life was moving around. Well, they come back and did it again with dust particles instead of pollen, those being inherently not life, and it did the same thing. So the Brownian motion was kind of interesting. So Einstein did the same thing, the same technique. We call it statistical mechanics. Statistical mechanics. He applies the statistical mechanics to basically the atoms and what we know about atoms of the time to analyze this. And he says, you know, if this behaves this way, then atoms have this roughly mass and have roughly this diameter, so on and so forth. Believe it or not, this paper was actually the nail in the coffin for the belief of atoms. So in this paper, Einstein basically proved the existence of atoms in such a way that statistically it would be such a level of luck if he got it right and he wasn't right, that it's sort of like the equivalent of winning every lottery for your whole life. So that was one of the things he attacked. The other thing he attacked was the electrodynamics. Electrodynamics of moving bodies. That was the special relativity paper. And that one really could have won the Nobel Prize as well. The Brownian motion one could have won the Nobel Prize. He also did the photoelectric effect. And that one, he was inspired by Plunk. So Plunk, in doing this analysis up here, he found that basically energy is given off as little packets of energy. Being h times f or hc over lambda as little photons of light, basically. So he used that to attack this problem with the photoelectric effect. And the photoelectric effect is basically, it's easier to see in a pure metal, so I'll talk in terms of pure metals, but if you take like aluminum or something like that, and it's not necessarily painted or anything, and you shine light on it and you attach a voltmeter to it or an ammeter to it, what you'll see is the light alone hitting the hitting the metal will actually cause a current to basically to develop in the metal. Okay, that's the photoelectric effect. It's a crazy thing, but Einstein, again, using statistical mechanics and this new idea of energy of a photon having a very distinct amount. And what he did was he made a plot of frequency versus, in this case, he was using frequency versus the frequency of the light. And basically, as you'll see, like or you might have saw in chapter 15, the energy of light is given by the square of the amplitude and the square of the frequency, right? So it turns out, and what did I say here? Oh, I wrote F on both places. This is the kinetic energy, sorry, of the actual electrons. So basically what he did when he did the statistical analysis, he found that there should be some minimum amount of frequency some minimum frequency, which obviously if this is a minimum, that gives you a minimum amount of energy. He thought there would be a minimum amount of energy it would take for you to pluck a electron off of an atom, which is what happens in the photoelectric effect, because the electron has to free itself from sort of the atom or the lattice in some sense, and then be able to move along in the direction of electric field. And he figured there was a minimum amount, and that would be dependent on the material that you're actually using, whether you're doing it shining light on gold or aluminum or copper or steel. And he actually made this wonderful equation, a straight line equation that looked like this. And he said this would be the frequency, and if we compare that to the molecule or the atom that's actually being used for the metal, then we can actually use that as a property of the metal, so on and so forth. And he said that the kinetic energy maximum, which is what we plotted here, this maximum kinetic energy that the electrons will have after they do their work to release the electron, or to release the electron from the atom, they will then have some kinetic energy given by h times f, where this is the light frequency that caused it, minus w0, where w0 is actually equal to h times f0, which relates to that. So there's this work function that you have to overcome just to loosen up an electron, right? And if you just give it that much, then the kinetic energy is just going to be equal to negative of W0, and I'm going to get no additional kinetic energy. This is supposed to be max. I don't know why I wrote Mac. So if you get above that work function, then all the extra kinetic energy, all the extra frequency and energy will go into the kinetic energy of the electrons. And lo and behold, when they ran the experiment, they found that he was exactly right. And this is the one he won the Nobel Prize for. But it also treats light as a particle, and it uses this Plunk equation, E equals H F, or E equals HC over lambda. I don't know why I never wrote lambda there. E equals HF or E equals HC over lambda to analyze how things behave. And that was really on the money. So he, gets really excited about this. He publishes it. And in fact, him and his wife are so confident that he's right, that he's going to win the Nobel Prize for this banner 1905 year, that he uses that as a bargaining ploy to get out of his marriage. He's no longer happy with his wife, and his wife's not happy with him. So they want a divorce, and he tells her, he said, well, I don't have much money. I'm, a lowly professor or whatever, actually a patent clerk. And he says, but if you let me go without having to pay you up front, then I will give you my Nobel Prize winnings. And she said, okay. And, it was a smart bet, because he did get the Nobel Prize, and of course she got the money. So that was kind of neat. But basically, this is the photoelectric effect, and it was a very important discovery, and it was one of the founding papers of quantum mechanics. So it's important in that way. So people were starting to say, okay, well, it looks to us like there exists light that can act as a particle, this little quantum of light, if you will. And I'm saying the word quantum, like in Quantum Leap, the show. So there's this little quantum of light where it basically behaves like a particle. And we already know that, from Huygens and from Maxwell and other people, that light very much behaves like a wave. For instance, the best example I can show you without having to use super expensive experimental device is just hold your finger, your index finger and your thumb prints really close to each other like this. You can even start to see it there, even with this crappy picture of the video. You're seeing blackness in between the thumbprints. And what's happening is each point between my thumbprint and my index fingerprint acts like a separate source of radiation. So each one of those little infinitesimal points creates a little wave of light, and it propagates outward like it's from a sphere. And then adjacent to that is another one doing the same thing. And adjacent to that's another one doing the same thing. And each of them have a wavelength, distance from the peak of the wave to the next peak of the wave, that's related to its color. So when you do that, what you see is these waves curving around like this. Sometimes the troughs line up with the troughs, and the peaks line up with the peaks. When you have that, you have something called constructive interference. And that can be allowing so much light through that you see a really bright spot on the light. But in other areas, you'll have the peaks lining up with the troughs. in which case they're canceling each other out and you get no light getting through, and you can see that. But if you want to see it yourself and the resolution of the camera is not good enough, take and do your fingers, get them really as close together as you can without them actually touching, and then look up at a light and you will see little prints of the outline of either your fingerprint or your thumbprint. I can see when I do it, I'm seeing right now, I'm seeing 1, 2, 3. So I close one eye. For some reason I get better vision. It looks like I can see 5 different lines. That is definitive proof that light is acting as a wave. We can't explain that with particles. Oddly enough, there are experiments that can do exactly that thing, and we can explain that with particles. We can't do it with our fingers because it turns out to do something, you have to have a very, very small amount or size of wavelength, if you will. So anyways, we can't do that right now. So we've got this dichotomy going on where we know a bunch of experiments work as light being a wave. And then there's all this new stuff coming along where light's a particle. And there's this person by the name of de Broglie, and I'm probably horribly mispronouncing his name, but it's Debrogie. And he has this neat background in that he's doubly noble. He comes from 2 noble bloodlines, like one from France and one from Austria or something like that. And he's in college trying to get a degree, which a lot of, wealthy nobility people were sort of advised not to do that because you're sort of creeping in on the poor people's territory. So you're supposed to stay away from that. In this case, he didn't listen to that. He was really interested. He actually was a brilliant guy. And he was going to get his PhD in physics, basically the equivalent of physics, whatever they called it at that time. And physics probably came around, the word physics probably came around in the 1800s as the actual word that we use for it. But there was, other things, natural philosophy and stuff like that. So the way the story goes is he is trying to get his paper published and his thesis done so he can get his dissertation done, i.e. his PhD. And rumor, again, this is rumor mill stuff that comes from generations of professors. It's probably all fake, to be honest with you. It's probably not even true, but I love the story, so I'm going to tell it to you and then let you do the historiography to find out if it's actually right. But anyways, supposedly his professors were like, this guy's really bright, but this crap he's come up with this crazy photon thing and this wave thing, I think it's kind of a nut job and I don't really want to put my name on it. And they said, well, we can't really just say no because he's, double nobility. We could lose a lot of money from this. But luckily, this was about the time Einstein had become famous as a result of his experiment Edgerton had run about the general theory of relativity, so 1915. So Einstein's on this world tour. He happens to go to the school where de Broglie is, and they asked him to take a look at this thesis. They said, hey, we're in a bit of a pickle here. We have this noble figure who has an idea, and he's really brilliant, but we think his idea might be a little crazy, but maybe you're bright enough you can figure out what it is. And he looks at it and tells them it's the most exciting thing he's seen in decades. So they immediately, of course, give him his PhD. But his idea is this. Basically, from the symmetry or the beauty that he thinks is necessary for physics to have, which I agree with, and so far we've always found it to be that beautiful. That's why they use titles like Elegant Universe and stuff like that. He said, more or less, I cannot imagine a world where God would create matter that behaves as both particle and waves, or waves that behave as both particle and waves, and not have the other one do the same thing. In other words, one's doing it. In other words, one has properties of waves and particles, and the other one should have properties of waves and particles. And based on that alone, he said that electrons, for instance, and atoms and humans and all this stuff would have a wavelength. And he said basically the wavelength would be h over lambda. So, the momentum would be h over lambda. So this is de Broglie, and I can never remember if that's capital D or lowercase d, but I'm writing it down here in a second, and I'm going to show it to you. So de Broglie had this hypothesis. So let me show you my document cam. And his hypothesis was that since light has wave and particle characteristics, shouldn't matter too. So that's his sort of hypothesis is, hey, if light has both wave-like characteristics and particle-like characteristics, I'm reminded of Kurt Vonnegut's drawing right here. Oh, that makes me laugh. Since it has these two behaviors, then it makes sense to him from a beauty standpoint, a symmetry standpoint, that the universe would not allow light to behave this dually without matter doing the same thing. So he said, and this is basically just working on units, you know, he said, if you find the momentum, say, of an electron, which classically is m times v, you can set that equal to h, the Planck's constant we just found, over lambda, and lo and behold, the units work out right. Okay. And that's more or less what kind of techniques you use often when you're introducing things is how can I combine things that I know are relevant to get the unit that I want? So he suggested this, and it turns out it's actually true also when we do the relativistic version, which is gamma minus 1 times mc squared is the momentum. So when you use momentum, it's supposed to be equal to h over lambda. Okay. Now, if you start talking about the momentum of an actual, say, electron, remember the electron mass is basically 9.109 times 10 to the negative 31st kilograms. So even if you're multiplying that times 100,000 meters per second, that's literally only 10 to the 5th. So you're not getting very close to anything sizable. It's going to be on the order of 10 to the negative 26th. In terms of units of momentum. So that's just way too small to have 6.63 times 10 to the negative 34th divided by that wavelength and get something appreciable. So it turns out in order for him to prove his theory correct, he has to actually be able to find something super small like an electron and have it go through something comparable in size to its wavelength. And from that, you can see its wavelength is so small. Later, we ultimately are able to confirm it, but we only can confirm it by using the space between the individual atoms in a material. So we shoot electrons through here, and they actually act like waves going between your fingertips. Remember how, you know, two adjacent spots will have a wave propagating outward like this and this, and where this crest and this crest are lining up, you're getting constructive interference, but where the crests and the troughs are lining up, you're getting destructive interference. And it's only when these distances between these things are like 10 to the negative 10th meters. But when they did that, they did, lo and behold, find that not only was Planck right about electrons having a wavelength, he was right about the formula for it. It's just h over lambda is equal to momentum. So when you take the momentum and you divide the Planck constant by the momentum, that gives you the actual wavelength of the light. So that brought us along a little ways to realizing, okay, not only does light and have these wave particle dualities where sometimes it behaves like a particle, other times it behaves like a wave. And if you haven't done that type of experiment before, you don't know what you're going to get until you do the experiment. This is one of the things that bothered Einstein. Einstein, like a Clockwork Universe, one where basically we call it predictive or something like that, where basically if you know all the forces acting on something and the velocity and mass that it has at any point in time, you should be able to predict any point in the future what it's going to be doing. That is a Clockwork Universe, and that's what Newton's laws gave us. It gave us a universe where we could predict things if we had the horsepower to do it. When you start introducing quantum mechanics, it doesn't work that way anymore. You don't know, for instance, whether a particular experiment is going to make the photon behave like a wave or a particle until you've already done that experiment. And sometimes, even if you tweak that experiment just a little bit, you get an entirely different result, which I can tell you about later. So that's some of the stuff we're seeing at this point. Then comes along, so that's de Broglie. This is Einstein. And of course, up there we had Planck, Max Planck, so we got that name already. So these are the big movers and shakers. Well, there is another problem in science at this time, and that problem they think is a chemistry problem, but they think it's a chemistry problem that when solved can really give them a lot of helpful tools in chemistry. Specifically, what they found out is if you take a little test tube, say a little test tube, and you suck all the air out of it, okay, and then you backfill it with a pure gas, let's say like hydrogen gas. Okay, and I'm saying I should put it in parentheses, that's the gas hydrogen. Well, they go ahead and take that and narrow that down and then put it on another sort of test tube, and then they close off the test tube and they put a ginormous battery, and it's not really a battery, but for all intents and purposes it's like a battery. You put a ginormous battery on here so that you can get on the order of 500 to 1,000 volts across that. Okay, when you do this with hydrogen, you get a very reddish colored line, and if you take that line and you shine it through a thin slit, and then you take that thin slit of light and shine it on a prism, then the prism will bend it out into what looks like parts of a rainbow, but instead of getting a complete rainbow, you get this dark space where there's very distinct different colors. So there's like a red, and then there's like a purple, and then there's like another color that's neither of those, and two more colors. And in fact, one element to another, these colors, their positions and their relative distances apart differs for each element. That's crazy. It's so ubiquitous that a middle school math teacher derives a mathematical formula for the very wavelengths, and that's what this is. Remember, when you spread a light out into a rainbow, basically you're spreading out according to its wavelength or frequency. Either one's equally valid to use. So these are various wavelengths: wavelength 1, wavelength 2, wavelength 3 and 4, wavelength 5, 6, because there's 2 there and 2 there, or excuse me, 2 there. So this, like I said, middle school math teacher at a local girls' school even derives a formula for it, but no one can make sense of why it's happening. Then comes along sort of the guy that most people who have don't have much more science in their background than, say, earth and physical science in high school. They think he's a one-hit wonder, but his name is Niels Bohr. And that's Niels Bohr from Denmark. He's from Copenhagen. And in fact, he is not a one-hit wonder. Everybody thinks he's a one-hit wonder because they hear about basically the Bohr model of the atom. And that's all they hear. But in reality, Bohr does this model of the atom at this point right here. And he goes on to foster the creation of quantum mechanics for the rest of his life, and in fact gets it to essentially where it is today, all more or less on his own, with Einstein helped a little bit, and other people helped, of course. Oppenheimer did some important stuff. Heisenberg did some important stuff. Pauli did some important things. All these people did important things, but the weird thing is most of them were students of Niels Bohr. So Niels Bohr really is the father. So his idea is this: hey, de Broglie says that electrons can be waves. We study a lot of waves in physics, so I wonder if it has to be a standing wave. So the problem was, we knew the plum pudding model of the atom, which was basically that the matter in general was sort of like let's give you a name that makes more sense in America, more like a raisin bread. Not a plum pudding, but a raisin bread. And in fact, a plum pudding is about the same thing as raisin bread. But that was the model of the atom that we had around the time of Rutherford's experiment, when he discovered Rutherford backscattering. So what they did was they were trying to figure out how the little raisins are distributed in the bread. So they took a little piece of foil, and in fact, it was gold foil, like aluminum foil, but made out of gold. And he was firing these particles. The biggest small particle we know of, called the alpha particle, it happens to be the nucleus of the helium atom. It's 2 protons and 2 neutrons, so 2 p's and 2 n's. So it's literally like 4,000 200 times the mass of the electron. The first particle we discovered, in fact, was the alpha particle, which is a helium nucleus. So we named it alpha. The second particle we discovered, we named beta because we're not that imaginative, and that turned out to be a positron / electron. And then the third particle we had discovered was the gamma particle, again, not very creative, and in that case, it turned out to be the photon. Okay, but at this time, this helium nucleus was the biggest thing we'd ever encountered, and they're firing these at high speed at this gold foil, and they're expecting, you know, the little bits of atoms to be floating around like raisins in a raisin bread, so you get little deflections here and here and here, but not huge changes, right? All the little particles would just fly off, and you'd have little detectors back here that look like soup cans that would pick up all these things, and then by looking at those trajectories, you could work back and figure out how the atoms and molecules, if you're dealing with a compound, for instance, how they're actually oriented in the material. When he did this, according to Rutherford, who's this brash guy, he's the one that says, science is physics, the rest is stamp collecting. So that's Rutherford. And he's working at Cambridge, and according to him, he was being a thorough experimentalist, and he made sure he took some of these detectors and put them around here just to be, you know, 100% certain what the outcome would be. His people working in the lab said, no, he just left one back there, and it made a beeping noise. We were like, what the hell's going on? And then lo and behold, we discovered that some were actually, these alpha particles were actually bouncing back and being detected back this way. They called that Rutherford backscattering. So that was a big deal. And in Rutherford's word, it was like firing a bowling ball at a 16-inch gun, and the 16-inch round bounced back at us. In other words, you know, a bowling ball is really, really small compared to a 16-pound projectile launched from a battleship. That's what they were talking about. And it would be really absurd to think a bowling ball would cause that big projectile to bounce back. And that's what's happening here, because this alpha particle is so big, and he's thinking there's little bits of electrons and protons and neutrons or something like that in here. It's very unlikely that you'd have one come bouncing right back. So ultimately, they had to abandon the plum pudding model. They got rid of the plum pudding model, and they had to make a solar system style model. And what they did was they imagined a very dense but small nucleus, and orbiting around it like planets orbiting our sun were electrons. So you've probably all seen this kind of diagram before. And this is what they thought the atoms were made of. And in fact, modern day analysis tells us that if the nucleus was scaled up to the size of a grape seed, you know, those itty bitty grape seeds that get between your teeth, how small they are, and you put it at a 50-yard line of the Washington football team's field, then the actual electrons would be out in the parking lot. So that's how small the nucleus is compared to the atom, but it still holds like 99.99% of all the mass, which is about the same ratio as the mass of the sun to the rest of the things. So this was the new model that we had for the atom. But the problem with that, and Bohr knew this as everybody else did, Maxwell's equations say that when a charged particle, which is what these electrons are, when a charged particle accelerates, and remember, acceleration means speeding up, slowing down, or turning. So even if they're going at constant speed in a circle, they're still accelerating. Well, if they're accelerating, then they have to give off radiation. And radiation means they lose some of their energy, which for an electron would mean it slow down. Well, if it slows down, then it's not going to be going fast enough to fight the attraction that the protons in the nucleus have for it. So it will, in fact, spiral inwards. And they calculated that hydrogen, which we now know is the most prevalent element in nature, that would last on the order of 10 to the -9th second, something like that. Okay, so hydrogen would be unstable if that was the case. So that's the problem with this model. It's great. It's got a nucleus, so that explains the backscattering. It's got a force holding them together. That's a force we're recognizing. Well, Bohr comes along and sees de Broglie's hypothesis as P of the electron is equal to H over lambda of the electron, he says, well, maybe the reason that these electrons aren't giving off radiation is that there's certain allowed orbits in nature where the distance around the circumference of the orbit happens to be equal to, so C equals circumference, is equal to 2 times pi times the radius of the orbit. What if those are only allowed if the 2 pi times r is equal to some number times the wavelength of the electron, where the number has to be 1, 2, 3, dot, 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 okay? He said, what if that's what nature has done? Nature has allowed electrons to not give off radiation due to their acceleration if there's certain allowed orbits, because they're actually waves that are just vibrating around the thing. So for instance, remember a wave looks like this. It also, of course, you could treat it like this, or you could treat it like this, or many other things. But the main thing is a wavelength is from a midline, skip one to midline, or from a peak to a peak, or from a trough to a trough, right? So if you imagine the nucleus is right here, then the innermost orbit should be exactly one wavelength around. So trying to draw this shape, I would make it on this side, and then like that. So that radius, that 2 pi times r is equal to n equals 1. So 2 pi r is equal to 1 times lambda of the electron. Okay. So the n is equal to the actual number 1 in n times lambda. So the circumference is actually equal to 1 times the wavelength of the electron. The second orbital would in fact be 2 wavelengths. So you'd sort of go like this, and then you'd be halfway under, and then quarter again, and then halfway under, and then like that. That would be 2 wavelengths. So this one is n equals 2, which means 2 pi r is equal to 2 lambda e, and so on and so forth. Well, he knew that Coulomb's law, which says k electron squared, the charge of the electron is the same as the charge of the neutron. So you can just call it E. And the force of attraction between the proton and the electron would be K times E squared over R squared, where R is the radius of the orbit. But that's also got to equal mv squared over R. And we also have to have that V is equal to 2 pi times R over the period. But we also need 2 pi r to equal n times lambda e. When you combine all this stuff, what you end up getting is an equation that happens to exactly match the equation that the middle school math teacher got, or the high school math teacher, basically the guy at the all-women's school math teacher got. Only this one has constants that we recognize from physics. And what the formula is, it says that basically 1 over the wavelength is actually equal to R times, in this case, there's actually several of them. There's a Balmer series, there's a Paschin series, and a Lyman series. But basically all it is 1 over n1 squared minus 1 over n2 squared, like this. And R is called the Rydberg constant. And in fact, R has a expression that we can make sense of once you actually do the derivation that your book covers in page 1003 and page 1004, where basically he ends up getting that the Rydberg constant is about Z, where Z is the atomic number, times Z squared, excuse me, times e to the 4th. Actually, I want to make sure that's the right one. I think that might be the wrong one. Let me see if I can get it up here in another place. No. Oh, wait a second. No, it's a different R. Crap. Well, what I gave you here was 1 over lambda. and I'm writing outside of the screen now, I just realized that. What I gave you here was 1 over lambda. Remember, the energy is equal to hc over lambda. So if you multiply this times hc, then you'll have the wavelength of the photon emitted from it going, say, from N2 to N1 or vice versa. So N1 and N2 is these N's. So this could be N1 and this could be N2, and N equals 1 or N equals 2. You could go from 1 to 2 or from 2 to 1. One would absorb energy, the other would give off energy. It turns out when you say E equals hc over lambda, then you get E is equal to hcr times 1 over N1 squared minus 1 over N2 squared. Now I can tell you in this, guys, that hc times r is actually equal to z squared e to the 4th m for the mass of the electron, 8 epsilon naught. That's the epsilon naught from Coulomb's law. Epsilon naught, and it's actually squared, times 8 squared. So we have this neat constant that, this equation basically is the same as the equation that the math teacher had found. And he had the numbers here, but he didn't really have any physical meaning behind this number. When you compare it in this way, you see, oh, wait a second. It's made up of the electron charge, the mass of the electron, that Planck's constant, and so on and so forth. And that's what, sort of like what Kepler did, what Newton did with Kepler's laws, is Newton invented gravity or discovered gravity, and from that was able to make sense of Kepler's laws and give the formulas actual symbols that meant something. Well, that's exactly what Bohr does. Bohr takes that formula that math teacher came up with and made it mean something by evaluating from first principles, using, Coulomb's law and centripetal acceleration times mass, work all that out, set the length around equal to 2 pi r equal to n times lambda, where n could be n1 or n2, any integer basically. And from all that, he got a way of seeing the atom. And our current model of the atom is, yes, a teeny nucleus, and then certain very much allowed radii. So there's R1, and the electron can be in R1 or R2, but it can't be in anything between R1 and R2. And stuff like this. So there's actually a distinct radius for each of these. There's a distinct energy for each of these. And in fact, when an electron, say, falls from here to here, it went from a high energy state to a low energy state. So it might have went from n equal, in this case, you can see n equals 3 to n equals 2. So basically what you're saying is the second case is 2. So this would be 1 over 2 squared, would be 1/4. And 1 over 3 would be, n being 3, it would be 1/9. So 1/9 minus 1/4, that actually gives you a negative amount of energy. So you should probably do it in the opposite order. But anyways, that gives you an amount of energy, and that happens to be the energy difference between this orbital and this orbital. So E3 minus E2 is equal to hc over lambda, which I'll call lambda sub 3/2, which means the transition, the photon given off by the electron transitioning from orbital 3 to orbital 2. If you take hc and divide it by that wavelength of that color, then you'll get E3 minus E2, but you'll also get hc times the Rydberg constant times basically 1 over 2 squared minus 1 over 3 squared. Okay. So that's a very big deal, because it turns out the electrons do in fact have a set level. This method he used is like the stepping stool I was telling you. It's like the universe left Bohr a little step stool where he can look over the counter and just make out what, mom or dad's doing in the sink. And he could see enough where he got this idea that maybe the electron having a wavelength means it acts like a standing wave. And that gave him the idea of thinking about things in terms of waves. And from that, he was able to put together an equation that actually matched exactly the wavelengths that were put off from that experiment for hydrogen. He does exactly the same process for helium, which is the second least complicated atom. And in that case, it fails miserably. So it's completely wrong. The whole idea is wrong, but it got them thinking about waves, because then Schrodinger can come along, and Schrodinger can come along and see that, well, we're thinking about waves, and waves have a very specific character. You might know of them as sine of kx minus omega t or something like that. That's a plane wave. Physicists often think of it as E equals h omega, which is really giving you the energy. And you could say, relate that to a wave. You could say h omega, where omega is the frequency here, minus kx or something like that. And when you take the derivative of E, you end up getting a h bar omega. And then when you take the derivative with respect to time, you end up getting a minus k is what you get for the d by dx, and what you get for the time is an omega. So you can start to see, oh, wait a second, h omega minus kt, or yeah, kt. So actually, I should have said h bar omega t times something like that. But anyways, when you took these derivatives, d by dt, you could see a relationship between the wave equation. So Schrodinger, just from looking at sort of this plane wave formula in exponentials, he was able to come up with an idea about the Schrodinger equation. And basically what he found is negative h bar squared. Remember, h bar is just h over 2 pi over 2m times d2 psi. Psi is this wave function we'll talk about in a second, over dx squared plus v times psi is equal to I times h bar partial of psi with respect to t. That's the Schrodinger equation. And you can put it together just by treating this as if it were a plane wave, doing the derivatives, and then you just have to add this potential part. Well, because Bohr got to look into the sink and think about a standing wave, that made everybody think about waves. And when Schrodinger thought of a wave, he thought of a wave equation. He thought of plane waves and how they would be basically, like if I wanted to pull out an h from this, I could do that, and you would have basically p times x over minus h omega times t, that sort of thing. From that, he was able to get the Schrodinger equation, which oddly enough, we had an answer. I mean, we had a equation for, but we really didn't know what this answer was. What the heck is the psi? It turns out, notice there's an I there. That's the square root of -1. That's that beast that's supposed to be an imaginary number and shouldn't have anything to do with an actual physical equation explaining reality. So ultimately, we are able, with the Copenhagen interpretation, to figure out that if you take psi and you do something called take its complex conjugate, which means literally A plus IB, remember that in real numbers, complex numbers, you had a real part, an imaginary part, and you could represent every number as the real part plus I times the imaginary part. Well, if you change that to A minus IB, then you've taken the complex conjugate. So basically everywhere you see an I, replace it with a negative I, and that'll be psi. And then you multiply that by psi as well. And then you multiply that by some differential volume element dV. Then it turns out this is exactly proportional to the probability of finding the particle in dV. So you actually have to take the solution from Schrodinger's equation, which may or may not be imaginary. You have to take the complex conjugate of it, multiply it by the function itself, and then multiply by that by dV. And it turns out that quantity is directly proportional to the probability of finding it between V and V plus dV. That was a really weird thing to figure out, but it turns out it's right. At the meantime, this was all Schrodinger, Schrodingger, famous from Schrodinger's cat. Okay, Schrodinger came up with this way. At the same time, Werner Heisenberg, y'all might know from Breaking Bad, Whoop, I just wrote Heisenberg. Heisenberg. Okay. So Werner Heisenberg, who was, by the way, a Jewish person working for the Nazi government at the time, we think we've got enough historical documentation now to show that he was sandbagging quite a bit because he knew the dangers of the Fuhrer. But that's, not really the physics of all this. But the interesting thing is that he was the lone brain left behind in Nazi Germany to run the potential nuclear plant program. And he certainly had the horsepower to figure this stuff out. Yet they didn't come up with a bomb. And we think ultimately it was partly because he sandbagged in a good way. And, it's pretty amazing that they kept him there despite the fact that he was of Jewish descent. I don't think he was a practicing Jew, sort of like Einstein. But either way, Werner Heisenberg comes up with an entirely different way of making quantum mechanics. And specifically, he calls it wave mechanics or matrix mechanics, where basically he says the only things that matter in the universe are things that we can measure. And he knows that when you go through this process of figuring out these probabilities, you have to multiply these values times each other. So he imagined an infinite matrix. So literally it would have an infinity of rows and an infinity of columns. And basically when you did, this element times this part of this element, that would give you the probability of transition from here to here. If you went from the second element to the first element, that would give you a probability from here to here. And from that, he was able to make an entire statement of quantum mechanics, all in these infinite matrices forms that later was able to be shown to be exactly equivalent to Schrodinger's equation. But the sad part was that way is really nasty and hard to deal with. So everybody just dropped that and ran away from it. And everybody went to Schrodinger. But it turns out there's a lot of good things that come from it. So for instance, we get the Heisenberg uncertainty principle, which basically says the uncertainty in the X momentum times the uncertainty in the X position is greater than or comparable to H bar over 2, I think is what it was. That's like a natural duh moment from Heisenberg, whereas it takes some work to show it from Schrodinger. So are obviously some great things about quantum mechanics that Heisenberg brings in with his equation, but they're basically using all this time, they're using something called the correspondence principle that Bohr actually introduced. And the correspondence principle basically says, hey, if you want to get rid of all these existing theories that we have in physics, if you want to say that Newton's now wrong regarding Newton's law of equation, which, general theory of relativity shows that in some sense he is wrong, right? Newton doesn't explain black holes. It doesn't explain gravitational radiation. And it even doesn't really explain the precession of the perihelion of Mercury as well as general relativity does. But what Bohr says is, hey, when we have an existing theory that works really well on a whole host of problems, and we're going to get rid of it by putting up some new theory, then his idea was this new theory better reduced to the old theory in the area where the old theory was correct. Okay. And that's sort of like a path that Bohr has given them to figure out how to make quantum mechanics. So they can take things like equations that we study in really highbrow mechanics, where we do something called Poisson, Poisson brackets, which is really what this Heisenberg uncertainty principle thing's about. We do these certain brackets and we get very specific results. If you do that in quantum mechanics, you should get a result that if you let H go to 0, then it better give back the result of Newton. And that was one of the tests, for instance, that Einstein ran on his general theory of relativity. And basically, he was able to show that it did produce the same gravitational potential and therefore the same gravitational force as Newton's law of gravity in the realm where the mass wasn't too huge or too compact. When it got too huge or too compact, then relativity had to kick in. Well, the same thing allowed them to forge on and press on. For instance, Schrodinger's equation, though correct, and you'll see it in your book, not in chapter 37, but more in chapter 38, that equation turns out to only be correct without regards to relativity. A guy by the name of Paul Dirac, it's P period, A period, M period. He's got like two middle names, sort of like George Herbert Walker Bush had two middle names. But Dirac comes along and uses basically the ideas that we've learned from Heisenberg, from Schrodinger, from Bohr, from Wolfgang Pauli, all these people. And he says, well, we need to make an equation for quantum mechanics that's consistent with relativity. And he does that. And when he gets it, it's amazing. It's this really simple, well, somewhat simple, but harder than Schrodinger's equation, in my opinion, to solve. He comes up with this really nice equation. But the problem is people are like, I don't think this equation is right because it gives me negative energies. And he literally says, no, my equation is right. There must be some existing particles that we are not familiar with, and I'll call them antimatter, so that for every electron that has a charge of negative 1.602 times 10 to the negative 19th, I suspect we're going to find a particle that is the anti-electron, we'll call it a positron, and it has a mass of 9.109 times 10 to the negative 31st kilograms, just like the electron, but it has a charge of positive 1.602 times 10 to the negative 19th coulombs. He's that cocky about how correct his equation must be that he predicts the existence of a matter that's never been seen before. And obviously he wins the Nobel Prize because he's right. So it's awesome. He becomes eventually the chair, the Lucasian chair of mathematics at Cambridge University. Again, the same position that Newton held, the same position that Maxwell held, the same position that later Stephen Hawking held, and now Witten, one of the co-inventors of string theory, is holding that position. So it's a really esteemed position, but it's kind of interesting that, you know, this equation is not even right. Once Dirac fixes it to make it consistent with relativity, then it's correct. And it turns out that that equation is so much like Schrodinger's equation. Unless you're dealing with really extremely fast things, you don't have to worry too much about it. But it's cool because Dirac comes up with these new ways of solving the Schrodinger equation. So that invents quantum field theory and all sorts of cool stuff. So that's really what happened. The only thing I really didn't mention was Compton. So Compton did something not unlike what Rutherford did. Specifically, Compton was running things into particles to try to see how matter was distributed within matter, or how particles were distributed within matter, stuff like that. So he did some work in that area. But what he found was something kind of interesting, that basically when he shot an incoming photon, in other words, you shoot a light particle at a massive particle, say an electron, then the electron will bounce off in some direction and the photon will bounce off in some direction. But here's the weird thing. The photon still travels at the speed of light. So unlike a car, you know, you bounce off the corner rear quarter panel of a vehicle, you are going 60, now you're going like 52, right? You'd expect that to happen. Well, photons don't slow down. So what happened was the photon comes in at one wavelength, runs into the electron, deflects off, and then leaves with yet a different wavelength. And the electron leaves as well with an energy. And Compton was able to calculate that the change in wavelength would be h times m sub e times c, the speed of light, times 1 minus the cosine of the angle that the photon is actually directed at. And I did a derivation of that on my YouTube channel. But really, those are sort of the equations you need to know. So I'm going to write them down right here so you'll know basically what you need, at least from this chapter. And you can see as you're solving problems in either the homework or the practice test. And I've made both the practice test and the actual test already available. So you can start on that at any time. We know that E is equal to HC over lambda, and we know that E is equal to HF. And H is, of course, 6.63. And you can carry extra digits if you really want, because your book gives it to you as 6.62606,896 times 10 to the negative 34th joule seconds. Okay, so we've got that equation, and that's the Plunk quantum hypothesis. We've also got, for instance, Einstein's two equations from the photoelectric effect, specifically HF, the energy of the incoming photon, is equal to the maximum kinetic energy that the electron has when it leaves the matter, plus the work function for the matter that the electron was bound to. So that's another equation we can use. You can also use, by the way, that K max is actually equal to E times the voltage. So the electron charge times the voltage that they're using to accelerate it. That comes in handy. We also learned about the Plunk equation, that big nasty 2 pi h c squared lambda to the negative fifth. I'm not going to write that down as something that you need to memorize, but there are occasions where you'll need it. So I'm going to write it down as lambda t is equal to 2 pi h c squared lambda to the negative fifth. So that literally means lambda is downstairs to the fifth power over e to the in this case, remember, it's hc over lambda. That's one form of energy. And then another form of energy, remember, is kT. So that's why it's hc over lambda kT minus 1. And that came from assuming that E equals some integer times h times f. In other words, this led to this. Make sure I got it written down right. Negative fifth, everything looks pretty good. That 5 is the ugliest 5 I've ever seen, but we'll deal with it. Beyond that, then we went into, of course, the de Broglie hypothesis, which was that matter had to have wave-like characteristics as well. And we say P, the momentum, is equal to h over lambda. That is the relationship for it. Of course, with a photon, it only has momentum and kinetic energy. It doesn't have any rest energy. So that's a whole different scenario that you deal with. Oh, and I should have been Wien's law. Wien's law says basically that the energy, or excuse me, that the wavelength of the peak of that curve, lambda peak, and it doesn't mean the highest wavelength, it just means the wavelength at which that curve peaked, is equal to 2.90 times 10 to the negative third meters times Kelvin over temperature of the object. Okay. So that was another equation I wanted to make sure you guys knew. You can even use that to get an equation for the energy, because once you find the wavelength, you can do hc over the wavelength, and that'll give you the energy. And you'll see that energy for a photon, E for a photon, is actually equal to 1.240 times 10 to the third electron volts times nanometers over the wavelength in nanometers. Okay, so this is basically another way of writing this equation, but instead of using instead of using Planck's constant in terms of joules, you're going to use Planck's constant in terms of EV, and your front of your textbook has that. The Compton formula, that's another one. Delta lambda, which is lambda final minus lambda initial, is actually equal to h over MEC. So it's Planck's constant over the mass of the electron times C times 1 minus cosine of phi, where basically what we're saying is a photon comes in, and I'll make it like an axis right here. How about that? What we usually mark a photon with is a little wave like this, and this is lambda initial, and then it hits an electron. The electron fires off at an angle theta, but the photon breaks off at an angle phi and has a wavelength lambda f. So that's what this is all about. If you take that angle, take the cosine of it, do 1 minus that, and then multiply it by that, you'll get the difference in the wavelength, lambda final minus lambda initial. And your book does a derivation of it. I did a derivation of it on my my YouTube channel, so you can check it out there as well. Basically, you are using momentum, but you got to use the relativistic momentum to get it right. and you can get the derivation. It's pretty straightforward. I'm not requiring you to do the derivation, but I want you to know the equation, that it exists, and know how to use it. We did that with de Broglie. Electron microscopes are just an extra thing you can manage. And then I did, of course, 1 over. So here's the deal. Remember I told you the different series. So there's a Paschke series, a Lyman series, and a Balmer series. And when you do the Balmer series, basically you're ending at the lambda equals 365 nanometers. So if you look at the figure on page 103, so Balmer, and that's actually the one that is mostly in the visible. And I mean the radiation in the visible part of the spectrum. That ends up at N final is equal to N equal, I wanted to say N equal 2. Is that right? Yeah, I think that's right. UV's higher energy. Yes. Yeah, there it is. So yeah, this is N equals 2. So you end up getting basically 1 over lambda is equal to the Rydberg constant times 1 over 2 squared minus 1 over N1 squared. So any transitions that start on an orbit N1 higher than 2 and falls down to 2, that makes a Balmer series. And then if you fall down to the 1 series, you're going to get the Lyman series. And this is in the UV, and that's N final is equal to 1, and you get 1 over lambda is equal to the Rydberg constant times 1 over 1 squared minus 1 over N1 squared. So notice it's the same formula, except instead of N final being 2, we had N final being 1. And then, of course, the N final, or the N1, I should be writing F on that to make it, or excuse me, I should be writing 1 on that, or I on that, to make sure y'all know it's initial. So I'll do it like that. In this case, obviously, N has to be 3 or greater. In this case, N has to be 2 or greater. N greater than or equal to 2. And in this case, N is greater than or equal to 3. And then finally, we have the Paschke series, P-A-S-C-H-E-N. And for that, we have N final is equal to 3. And we have N initial is equal to 4, 5, 6, ... And again, it's 1 over lambda is equal to R times 1 over 3 squared minus 1 over Ni squared. So that's part of basically the Bohr model of the atom. Gives of all these constants. The Rydberg constant, I wanted to write it down for you. It's in the, you can find it in your book anyways, but ultimately it turns out to be, let me see if I can find the darn number. Anybody? Oh, there it is, 1.097. 0974 times 10 to the 7th reciprocal meters is the unit, and that's the Rydberg constant. Okay, but from that you can see basically how we know the things we know about stars. So when we look at a spectrum from a star, it would normally be a whole rainbow because it's got a core that's really hot, just like the horseshoe stake that we threw in the fire. So if you throw a horseshoe stake into the fire, it'll slowly get hot enough where its radiation comes into the visible part of the light. Everything above 0 Kelvin produces radiation in a part of the spectrum that's reminiscent of its temperature. In the case of a iron spike, like a horseshoe stake, it's going to slowly turn a dark red, and then it'll go to an orange. And if you get it hot enough, it'll actually get white hot. And that's when it's extended beyond the violet end of the spectrum and gone on into the UV. And when you watch, for instance, rockets take off, their thrust at one point comes transparent. And that's really where the light is so hot that it's in the UV, and you're not seeing visible light specifically because it's gone so hot. So that's really what these different energies are. And when we're trying to figure out, for instance, that a star is putting off radiation, we know that inner core is a hot, dense object because the outer part, we know, or should say, we know the core is a hot, dense object, and the outer part is a lower density, cooler gas, because Kirchhoff's laws say that if you have that type of scenario, then the stuff coming out of the hot, dense core would be the complete rainbow. It'd be that whole curve that Plunk predicted. But as it goes through the cooler atmosphere, the individual atoms and molecules in that atmosphere can steal very specific energies that match, say, the energy from the first orbit to the third, or energies that match from the second orbit to the fourth, or from the second orbit to the third, but only those allowed energy values. Each of those energy values has a very specific wavelength. Therefore, it has a very specific color, and you'll see little black spots in what would otherwise be a beautiful rainbow. Those black spots, every set of them corresponds to a certain element or compound. And because Bohr made that discovery about how the atoms have allowed orbits that depend on the atomic number, that is a chemical process that we can now use to make sense of what the elements are. Okay. It's fine if you have to leave. The time is now 1 minute past. I just wanted to finish by saying, basically, that is how we now can look at any light coming from, a comet hitting a planet, or looking at light coming from a star, and we can tell not only what its temperature is by the Wien's law. We can also use other ways to determine the temperature even more specifically. We can determine exactly what elements are present and in what proportion. We can not only tell, that it's hydrogen, helium, carbon, nitrogen, all this stuff, but we can tell what percentages of each of them are from these Plunk type curves with holes in them. So that's the big thing that Bohr brought us. And you can look at it again from the standpoint of the Bohr model of the atom and see that you don't have to actually say the wavelength around is 2 pi r. You can actually set the angular momentum equal to a number time, or an integer times the Planck constant, and that'll give you the same results as Bohr did as well. So anyways, that's it. That's all of chapter 37, in fact. So next time we can do 38. And like I said, I'm not going to cover it all in detail. I'm going to do bits and pieces of 38 and 39, but you can check out the rest of it on my YouTube channel, and you should, to try to make sense of this. What we're going to find out is there's a, uncertainty principle, all that good stuff. I'm going to tell you how we can define how atoms behave. I'll tell you about Pauli exclusion principle, and, show you how to use the Schrodinger equation, that kind of thing. Everybody is completely free to go, but I'm waiting for the last person to leave before I do. So you folks have a good evening, and thank you for coming.
So you told that you posted practice test 7?
Yes, and I was telling them before you got there, Maria, sorry, or was that Maria? I think it is. Anyways, I was telling them that basically my syllabus said I'm going to drop your one lowest online test. What I decided to do was go ahead and give one more test, and now I'm going to drop 2. So it's, in some sense, you don't have to do it, but since the final could include part of it, then you probably should do it, and it's no way it can harm you. If you make a grade lower than one of the other grades you had, then that other grade will stay, and you won't even count this one. But you have an infinite number of tries as long as you get it done by the due date, which is a week from Wednesday. So you can actually bring your test score up even more.
So there is no practice test. But
yeah, the practice test should be already up. I did that even before I put the test. Let me double check and make sure I've got it up there for you.
I don't see it.
Oh, okay, it's there, but I didn't publish it. Now it should be seen. You should be able to back out and look at it again.
Thank you.
And I also went ahead and just made the practice final exam available to you guys.
Thank you so much.
You're welcome, sir. See you, Maria. Anybody else have any questions?
Yeah, I just wanted to solidify. The final was on May 5th, correct?
Yes. So we meet on Mondays and Wednesdays. We could, in principle, have it as late as the 10th. But my plan was to go ahead and try to knock it out on the 5th.
Gotcha.
If you need to take it earlier or later, let me know. That might be something I can work out for you. But the main thing is you've got to have your Respondus monitor available so we can actually use Respondus to monitor you through your webcam. And you got to have your Respondus lockdown browser work. Otherwise, you'll have to make an appointment at the testing center and test it at their convenience,
Gotcha.
not your own. Okay?
Thank you.
No problem. Anyone else? Jamie, Sean?
I had 2 quick questions.
Go for it.
On the last practice test, I think the highest grade you could get was a 97.5.
Yeah, that was one that lost a question, so I will correct.
Yeah, I noticed that. Okay,
Yeah,
thank you.
Some of my banks is weird. Like a question will just stop working out of a whole bank of questions, and I don't know.
Yeah.
So thanks for letting me know about that. And that was the test 6, you think, the practice test 6?
Yes, that was test 6. Yes.
Okay.
Practice
Well,
test 6.
Read over chapters 37, 38, 39, and even if you just skim them and start taking that that actual test after you take the practice test, and you might find that this latest test will help you a little bit more. But the practice final exam is up as well as that last test.
And then I had one more.
Yeah, go, Sean.
It's on mastering physics.
Mhm.
So I just wanted to clarify which ones are extra credit and which ones are like required to do.
Okay, so right now I think what I have as extra credit actually has the word extra credit on it. And since I'm going to go and rely on you guys to cover chapters 37, 38, and 39, that should include those chapters. I'm probably going to at least add one more homework problem set that I'm going to throw out. In other words, count only the 30 highest, or count all but the 3 lowest, or something like that. So I'm going to add an extra test just in case people feel a little rushed at the end of the semester and don't want to try to fit 3 chapters in this week. So if you don't get 3 homework chapters done, it's not going to be that big a deal, because I'm going to add yet another homework that I'm going to not count.
Yeah, that's the only reason I was asking, because it looks like I'd have what is that, 4. So yeah. Okay.
Yeah, if your test grades are good enough level that you think you can do about the same on your final and be happy with your grade, then yeah, you don't need to waste any time, especially on chapter 29. I doubt much will come from 20 or 39, but chapters 37 and 38 are probably ones that you shouldn't skip.
Okay. Thank you.
Okay. No problem.
Have a good night.
You too, Sean.
And I have one more question. So
Yeah, Maria.
the final will be based on chapter 29 through 39, right?
21 through 39, yes.
Okay, thank you so much.
No problem. Oh, Maria, didn't we do some thermo too? Yeah, I think we did. No, that was 131. No, we did. I don't think we did thermo in addition to that. Did we, Jamie? Do you remember? Did we do like chapters 17 or 18, or am I remembering 241?
Yeah, it says chapter 17, so.
Okay, yeah, that's in it too. Yeah, so we remember we did like 17, 18, and 19, but there's only a little bit of the second law of thermodynamics done. And but that was all done after we did 21 through 30, and then came back to that, and then came back to 37. So
Okay, thank you. Bye.
You're welcome. What's going on, Jamie?
I was actually listening in to see if any of the questions had.
I think I got the confirmation letter from ODU about doing a letter of recommendation for you. So I should be able to do that this week.
All right, thank you.
No